Right? I'm pretty sure the boss will kick me out of the lab this time.
Why? What's wrong? You drink too much coffee?
No, it's never enough. No, it's my algorithm. I mean, the optimization is great, but the optimized circuit is not even equivalent to the original one.
Then it's not good.
Yeah, I was expecting that.
You know which operation is wrong?
No.
Can you maybe draw down part of the circuit and do it by hand?
This benchmark is like super big, and I mean the algorithms work just fine for the small benchmarks. Only this one failed. Only this one.
It only fails on the big benchmark, so you cannot try on the small ones. Yeah, that's hard to debug. I can try to help you later, but I need to finish this first.
Thanks.
Wait, what?
What?
Someone said our tool has a bug, and he wants me to debug for him, but he couldn't give me the benchmark he used because it's confidential. You know, it's commercial secret. How can I debug if I can't even reproduce the bug?
No. Like it's so hard as logic synthesis developer.
Hello, the IWLS community. Are you a logic synthesis developer? Of course, I think most of you have developed or at least used some logic synthesis tools. How do you make sure if the implementation of your algorithm is free of bug? And when there is a bug, how long does it usually take you to trace and eventually fix the bug? I'm Siang-Yun or Sonia from EPFL, and today I'm going to introduce an automated testing and debugging toolkit specialized for gate-level logic synthesis tools. Software testing and debugging are in fact well-researched topics on their own. Among the many testing techniques such as unit testing, manually generated corner cases, regression testing, etc., there is a surprisingly simple but very powerful technique called fuzz testing, or fuzzing. The idea of fuzz testing originated in the 90s. On a stormy night, a developer connected to his workstation with a dial-up connection. Due to the noise in the connection, some random characters would appear in the command line even though he didn't type them. And surprisingly, these spurious characters caused the Unix system to crash. This phenomenon made them rethink about the reliability of their system and also inspired them to propose the fuzz testing technique. The idea is very simple. Stress test the system with randomly generated inputs. Yet it is practically very powerful. As for debugging, imagine when you get a bug report to fix, what steps would you take first? In the usual cases, you will first try to reproduce the bug. And once you have a failure-inducing test case, which means an input to the algorithm that triggers the buggy behavior, you might want to minimize its size because, like in the motivating drama in the beginning, when the failure-inducing test case is too big, it may not be easy to focus on the buggy part. Delta debugging is a technique to automatically isolate the failure-inducing difference, or the delta, between a passing test case and a failing test case. A simpler version of it, called minimizing delta debugging, automatically minimizes a failure-inducing test case. The basic idea is to remove half of the test case and test again to see if the bug is still triggered. If so, then we continue to try removing another half of the test case. Otherwise, we try the other half. And if it doesn't trigger the bug either, we increase the granularity and remove only a quarter of the test case. Automated testing and debugging tools are actually quite common in other fields like compiler construction, but they seem to be not yet a common practice in the logic synthesis community. So, in this work, we aim at providing a toolkit for testing and debugging gate-level logic synthesis applications, such as ABC, MockTurtle, and LS Oracle. The principles behind our toolkit are similar to fuzzing and delta debugging, but the algorithms are specialized for logic synthesis applications. To be more specific, the input to the algorithm is a gate-level netlist, such as an AIG or an MIG. For fuzz testing, besides purely randomly generated networks, we also propose methods to generate networks based on their topologies. We can enumerate all the small DAG topologies and randomly generate some networks for each topology, or we can also compose several small topologies together to generate a bigger network. These methods may be helpful in detecting bugs that depend on the certain topology. For debugging test case minimization, we propose a specialized algorithm to minimize a network that makes a logic synthesis algorithm fails on some given test. It tries to remove parts of this network, tests it again, and only keeps the removals that preserves triggering the bug and failing the test. The removal operations are designed for logic networks. It begins with removing larger parts of the network, such as substituting a primary input with a constant and thus simplifying its output logic, or removing the entire cone of a primary output. And then gradually it removes in finer and finer granularities, until there is not a single gate that can be removed and still preserves the buggy behavior. We call the resulting network a minimal core for this bug, because none of the operations can be applied to further reduce it. We do not adopt the binary searching scheme generally used in delta debugging because it is not very intuitive to define the complement of a network that still makes sense. Now, I will demonstrate the usage of our toolkit to give you an idea of how it works. The implementation is in the C++ logic synthesis library MockTurtle. You can find some ready-to-use code in the example folder. Let's say I have just implemented this algorithm called AIG resubstitution, and it passes some simple unit tests. I want to make sure that it is really correct and robust, so I can use the fuzzer to test it. In this fuzzing code, first we have a lambda function representing the oracle. It calls the algorithm and does some tests. In our case, it performs combinational equivalence checking. And then we will specify a random network generator and some parameters and run the fuzzer. The fuzzer takes the oracle lambda function as an argument and can call it later on different networks. Now we compile it and run it. The fuzzer simply generates a lot of random networks and calls the oracle. It stops when the oracle's test fails. So here we actually found a bug, where the optimized network is not equivalent to the original one. We can also visualize this network very easily with the example code draw. In fact, this is a real bug that I found when working on this paper and was reported on GitHub. Next, I will demonstrate the test case minimizer also with a real use case. Some time ago, someone reported an issue that an algorithm is endless. And when we look at the test case they provide, well, it's kind of big. Let's try to minimize it first. So I'll first copy the file to my working directory. And in the example code minimize, similarly, we have a lambda function as the oracle. I have changed the code to call the algorithm we are debugging. But for the return value, because the buggy behavior here is an endless while loop, I will measure the time and I will say normally it should not take too much time. And to make sure that the loop will end, I will force a maximum number of iterations. Now we compile it and run it. we can see that the test case is minimized from 349 gates to 23 gates. If we try to visualize the original test case, you can see it's not very readable. But the minimized one is actually much better. Again, these are both real bug reports that we have on GitHub, showing how the toolkit helps in identifying bugs and helps in the first steps towards fixing the bug. Yes, simply minimizing the test case doesn't actually fix the bug, but it makes the developer's life easier. Some of these bugs are already fixed, and the others are on the to-do list. We analyze and keep an eye on all of these issues. Although there are already an AIG fuzzer and delta debugger provided in the Agar repository, there are two key highlights of our toolkit. First, it can be used for not only AIGs, but also any other logic network representations such as XAGs and MIGs, which was not possible before. Second, it is tightly integrated in MockTurtle, so if you are debugging an algorithm implemented in MockTurtle or in a tool that is built with MockTurtle, you will benefit from a 10 times speedup over interfacing your algorithm with an external tool, such as the Agar utilities, because we don't need to always write out the network and read it back in. In the last part of this video, I want to share with you a case study on a real historical bug existing in MockTurtle. So perhaps some of you have noticed there are two implementations of code rewriting in MockTurtle. The first one, code rewriting with compatibility graph, was implemented first but has a bug. Because the fix for the bug will impact the efficiency and because the bug happens very rarely in our experience, we decided to keep this algorithm as is and implement a second version that is bug-free. The first reported test case that triggers the bug looks like this. The buggy behavior is that after applying code rewriting, the network becomes cyclic. From this somehow big benchmark, it's not so easy to identify what the core of the problem is. Now, let's use our test case minimization tool to reduce it. You can see that the network becomes smaller and smaller, like we're zooming into the network and finally find this core in it. And now I can tell you what happened. The algorithm identifies that node 7 XOR node 2 can be used to substitute node 11. And also node 11 XOR node 2 can be used to substitute node 7. This version of code rewriting uses a compatibility graph to find all compatible substitutions and apply them all together. And because it doesn't check for this interdependent case, both substitutions are accepted and leads to a cycle. This is an example showing how the test case minimizer is useful for identifying and tracing down to the core of the bug. Moreover, this case study also shows how fuzz testing with networks other than AIGs is beneficial. As you may have identified, this core contains two XOR functions, which is a key point for triggering this bug. If we randomly generate small AIG networks, the chance of generating two XOR functions and arranging them in a certain way that triggers this bug is extremely low. However, as the algorithm also works on XAGs, if we generate random XAG networks, the probability of hitting this case becomes much higher. The buggy code rewriting algorithm has been tested with unit regression tests and with many common benchmarks without showing any problem. This failure-inducing core, which is the only one we know until now, happened to appear only in the wild. If we would have fuzz tested the algorithm back then, maybe we would have caught it. Software debugging is one of the hardest problems developers face. It is estimated that more than 50% of the development time and budget are spent on fixing bugs. In this video, you have learned about a new toolkit in MockTurtle that can be easily used to test and debug gate-level logic synthesis algorithms. It is the first implementation of such toolkit that works on logic network representations other than AIGs. So it can also be used to test and debug algorithms for MIGs or XAGs. Another interesting use case of the test case minimization tool is that if you work for the industry and need to communicate a bug report that fails on a confidential benchmark, you can minimize it first with our tool. In most cases, after minimization, the resulting network is highly disrupted and can't be recognized anymore. It also makes the developer's life much easier if the test case you provide is not too big, so that we can focus on the only one operation that causes the bug. We advocate that such testing and debugging framework should be part of any logic synthesis tool and should become a common practice in the development of new algorithms and in communicating bug reports. I hope you enjoyed this video, and I welcome any questions or discussions.